Today it's my pleasure to introduce the 2010 College of Engineering Distinguished Lecturer, Professor Irving Bigio. This lecture series was created several years ago to honor our most distinguished senior faculty for contributions to the field and to our community. Since February 2001, Dr. Bigio has been a professor at Boston University in the departments of biomedical engineering, electrical and computer engineering, physics, and medicine. I want you to add English literature to that. He is also an honorary guest professor at the University College London, Department of Surgery. Professor Bigio received his PhD in physics from the University of Michigan in 1974, specializing in nonlinear optics. From then on until 2000, he was a member of the scientific staff at Los Alamos National Laboratory in New Mexico, including service as leader of the Laser Science and Applications program from 88 to 94. During various leaves of absence, he was a Fulbright Senior Scholar at the Weizmann Institute of Science in Israel, a visiting professor at the University of Copenhagen, Denmark, and a guest fellow of Pembroke College at the University of Oxford, England. He has over 130 publications and 6 patents. Now, during his first 12 to 15 years after his PhD, Irving worked on nonlinear optics and laser physics. During this time, he became well known in 2 major areas. One, for being one of the pioneers in nonlinear phase conjugate reflection, and 2, for developing a method for controlling the beam quality and wavelength of large, high-powered lasers. Several laser companies since have developed industrial lasers based on Professor Bigio's design. Since the mid-'80s, Irving has worked on biological and biomedical applications of lasers and optical techniques. His early spectroscopic studies focused on nonlinear excitations called solitons in hydrogen-bonded chain molecules, for example, proteins and DNA. In the early 90s, he was the first to suggest that ultrastructural changes in subcellular microstructure could be sensed by a non-invasive optical method called electroscattering spectroscopy, and that this method could be used clinically to detect early precancer by simple measurements mediated by optical fibers through endoscopes, catheters, or needles. Since then, there has been a large growth in research on this method and its variations by many groups. There have been conferences and books published on the topic, and a variety of clinical studies have demonstrated the promise of such novel diagnostic tools. This, in fact, project is deeply embedded in our Coulter translational program. In addition to those translational studies, Professor Bigio's current research also includes optical methods to study very early phases of apoptosis in cells and to non-invasively image nerve impulse action potential propagation in nerve fiber and brain tissue. Irving is an inventor on a number of patents in biomedical optical methods and instrumentation. He's received 3 R&D 100 awards for the development of biomedical optical devices. He serves on several government advisory panels and on external advisory boards for companies, academic institutions, and editorial boards in scientific journals. He's a fellow of the Optical Society of America and the American Institute for Medical and Biological Engineering, and a member of the American Physical Society and the SPIE. In addition to other research projects in biomedical optics, Professor Bigio recently led a multinational 6-year program under the NIH-NCI, that's the National Cancer Institute, Network for Translational Research in Optical Imaging, comprising several medical research centers in the United States and Europe. The spin-offs from this program are leading to new developments in a range of basic and clinical applications that include improved methods of screening for colon cancer, a method to monitor the earliest stages of apoptosis in cells, and novel methods for drug delivery in brain tumors. As a fellow of the OSA, Professor Bigio has served as a president's traveling lecturer for over 10 years. In this capacity, the OSA supports his travel to lecture at local sections and student chapters around the world, and in 2009 he was invited to give the plenary talk at the OSA annual meeting, specifically to honor him and to highlight his service in the traveling lecture program. Additionally, Professor Bigio was selected as one of 4 invited speakers for the Hot Topics plenary session at the BIOS meetings in January 2010, the largest meeting in the field in biomedical optics. Now, with all that, he's still a hero in my mind for another reason, and that is because he had the guts to take over senior projects in biomedical engineering after 23 years of me doing it. You couldn't have paid me enough to do that. It's my pleasure to welcome Professor Irving Bigio.
Wow. Will the real Irving Bigio please come to the podium? No? Okay, well, I'll do my best. So I must start off by, of course, saying that I'm very honored to be here because it really is a recognition from my colleagues and peers in the College of Engineering. And given that I follow in the footsteps of such luminaries as John Balliol and Mal Teich, these are hard shoes to fill and large footsteps to follow. I was also told this is a general public lecture, and friends and family are here as well as my colleagues. And so I'm going to try to present to you some aspects of our research that shall be palatable regardless of the math and physics that I'll tell, but I'll also try to introduce a bit of math and physics so that my colleagues can know that I'm for real and that we're really doing some science here. And so the first thing I'm going to do is explain to you why this theme of Van Gogh was chosen for the poster. And it's because Van Gogh might have been the first person who really understood light scattering. And that's evident in the way he depicts stars here. And clearly, you know, if you look out on a starry night, maybe not very often in Boston, but definitely very often where I used to live in Los Alamos, New Mexico, in the mountains, one might think that the stars are little tiny pinpoints, whereas he properly understood that they're really spread in effective size due to scattering in the interstellar space dust and the atmosphere on their way to us on the Earth. He also obviously was aware of what astronomers were seeing in the mid-19th century before they had cameras and digital imagers or film cameras. They were drawing what they saw through telescopes, and they saw the first observations of spiral galaxies. And so it has been surmised that Van Gogh was aware of that. But it pervades a number of his paintings. So you notice here in the scene of Café, a night scene of Café in the city of Arles, that the detail and resolution of things that he painted in the foreground is fine and highly resolved, but the stars are again fuzzy, scattered items. And my favorite of all is the Starry Night over the Rhone, wherein nearby lights, like the lights in houses there, are fairly well defined, but the stars are fuzzy and scattered. And so the question is, if we were to understand what causes the light traveling through the medium before it gets to us to be scattered, we may learn something about the scattering medium itself. So before I tell you, I'm going to explain also the title of my talk in a few minutes. But before I get there, I want to tell you how I got to work in this area altogether in the first place. So as Ken told you, there was a period of time when I managed the Laser Science and Applications group at Los Alamos. And so when people would call in to ask for information at the laboratory, sometimes the PR department would direct them to the science expert in that area. So I got this phone call from a gastroenterologist who said, you know, I'm doing colonoscopy in my patients who have ulcerative colitis. That's a condition where you have large areas of inflammation in the colon, and if areas of dysplasia, precancerous condition, develop in ulcerative colitis, they have to be treated because they can readily lead to colon cancer. So he said, well, I go in and I do random biopsies to see if there's any dysplasia, any precancer, and I'm just blindly cutting bits of tissue and sending them off to the path lab, but I'm probably missing areas where there might be precancer. So he wanted some sort of a magic laser that he could shine through his endoscope and look on the wall of the colon and find out where the early areas of cancer might be. And this seemed like a good idea, but we had never looked at this before, so we decided we were going to look at what other people were doing, and so we studied the literature. And so, of course, when you study the literature, you find out there was nothing that you ever invented. Did I go too fast on this? Let's see. Okay, so, and what we did find that there were a number of people working in this field, and I'll tell you about that in a moment. But then I asked the doctor, well, why do you want this laser? So I want something to be non-invasive. And so we asked, okay, and my students are going to groan because they've seen this slide 35 times. But so I asked them, well, what does non-invasive mean? And said, well, the medical definition of non-invasive is that you don't administer a foreign compound to the patient and you don't violate an organ barrier. So I said, let me see if I understand what you're saying. This means that if you give a patient an aspirin, it's invasive, but colonoscopy is non-invasive. Now, having just suffered through colonoscopy a couple of months ago myself, I can tell you the doctors have it all wrong, at least from the experiential point of view. The science point of view, there's good reason for this definition. So we were looking in the literature and we noticed that fluorescence was what most people were studying. They were studying autofluorescence, meaning the native fluorescence of the tissue's chromophores. So chromophores that are in the tissue that could relate to metabolic states in the tissue. For example, things that govern the energy cycle of the cell, that they could therefore be related to the energy cycle and therefore metabolic rates and could relate to cancer. And so they studied fluorescence, and that's what most of the people were doing. Some people were trying to administer drugs, which is of course invasive, that would concentrate in areas of fluorescence and be succinctly distinguishable from other sources of light in tissue. And then there are other types of spectroscopy that I won't go into, but Raman and infrared absorption spectroscopy that various research groups were investigating, which had the limitations that they're just not clinically friendly. They work great in the lab, but it's really hard to make them work well clinically. So just in case you want to know what fluorescence looks like, so this is a purple laser. You can hardly see it here because it's on the very edge of the visible spectrum, but if I shine it through this ball of fluorescein, you can all see that it fluoresces fairly brightly. And this is the stuff they squirt in your eyes when they want to look at, when you go for a general eye checkup. You can also, it's also FDA approved, so sometimes doctors will image perfusion, blood vessels in tissue in vivo by injecting fluorescein. But we decided we wanted to look at something different, and how did we come about this? Well, of course, we came about it by accident. We were studying fluorescence of tissue because we thought we could do a better job of it than what people were doing. We thought we understood more about the instrumentation and technology. And while we were studying the fluorescence, we noticed that the light we were trying to block, meaning the backscattered light of the excitation light, the short wavelength light, actually was more informative than the fluorescence that we were trying to measure. So this led us to develop this method called elastic scattering spectroscopy, which I will refer to as ESS a few times along the way to make it easier to not trip over my own tongue. But I want to point something out to you. It was brought to my attention by Shamar Amili, a colleague in the physics department. In case you think that biomedical spectroscopy is a recent thing, the very first paper ever published in Physical Review. So I want to point this out. This is volume 1, number 1, page 1 of Physical Review, is a study of the transmission spectra of certain substances in the infrared. And notice that 2 of those substances are oxyhemoglobin and chlorophyll. So these were the first optical spectroscopists. So let's understand first what goes on when light impinges on tissue. Let me see. Yeah. Okay. So there are a number of things that can happen, some of which are trivial and simple. Light can simply reflect off the surface, or it can scatter around a few times and get absorbed. It just might encounter something that absorbs it. Or it might scatter around a few times, get absorbed, and something there, some molecule there, might re-emit a longer wavelength photon. That's fluorescence. Or it may simply scatter around and come out as a glow, just like well, if I use the red laser, you can see it more easily. So you can see the light coming around my finger and also going through. That's just a red pointer laser. So it might simply go all the way through or get lost in the tissue or come back out. And so the question is, can we learn something by studying this little dance that the light does in the tissue before we detect it? And so this leads back to the title, which There have been various literary references over the years to skipping the light fantastic or tripping the light fantastic. They all hark back to John Milton in Allegro, which from the section of his poem about the dance of a forest nymph in the woods. Light-footed, delicate dance of a forest nymph in the woods. Come and trip it as you go on the light fantastic toe. In this case, the word light means delicate. We can use it with a double entendre here. But the question is then, can the light dance of light, or the gentle dance of light in tissue, enable a kinder, gentler method to detect disease, meaning non-invasively? So can we study the way this forest nymph dances through the woods and learn something about the trees, whether the trees are healthy or diseased, by looking at her dance? So we need to understand a little bit about the optical properties of tissue in order to do this. And there are two primary optical properties that we're interested in that govern the transport of light in tissue. So absorption, which is due to various chromophores, compounds that absorb light at different colors, and the fluids of the constitutive tissue, and also scattering, and in particular scattering, due to gradients and discontinuities in the refractive index. The word is missing there. The refractive index, or otherwise meaning variations and gradients in the density, because refractive index frequently, generally, typically follows optical mass density. So in tissue, transmission and reflection are dominated by the scattering properties. Even when there's strong absorption, the actual propagation of light in tissue is dominated by the scattering properties. So which process dominates over a modest distance depends on the wavelength. So at some wavelengths, at some colors of light, the light will scatter multiple times, and just work its way out or work its way deeply into tissue and only infrequently get absorbed, as in the case of red light. It just scatters a lot, but somehow gets out through my finger. Or if absorption dominates, then it might scatter a small number of times, but most of it will be absorbed and never quite make its way out, as in the case of this green laser, which just doesn't get through my finger, even though there's plenty of light here. So we then ask the question, well, what do pathologists look for? Pathologists aren't looking for the fluorescent properties of tissue, not 99.9% of the time, and they're not looking at the biochemistry, again, not 99% of the time. They're looking at micromorphology changes. So they're looking at and these are oversimplifications of a physicist, of course. They're looking at changes, for example, in the size of the nucleus compared to the total cell volume, the ratio of nuclear volume to cell volume, the variations and pleomorphisms, the variations in shape that are changed from what might be a normal cell. And then we ask the question then, how can we spectroscopically make a measurement that relates to these micromorphology changes, which is what a pathologist is looking for? And so, well, it turns out that photons scatter off of these gradients in the index of refraction. So if the nucleus is either higher index of refraction or lower index of refraction, the fluid around it, or the mitochondria or other organelles in cells are either more dense or less dense than the surrounding medium, that will be a source of scattering light. In the same manner that a water droplet in a cloud will scatter light, or a water bubble in water, a bubble of air in water will scatter light. So we proposed elastic scattering spectroscopy as a method of monitoring this delicate dance of light in tissue and trying to extract information about the architectural details of the tissue. And so what are some of the actual numbers? The index of refraction of water at around 500 nanometers in room temperature is close to 1.33. You'll add some salts and sugars to it and it goes up a little bit in index of refraction. The intracellular fluids is a little bit higher than the extracellular fluid. Proteins, lipids, DNA have larger values of index of refraction, but those question marks is because it depends on what you read in the literature and also on the tertiary structure. So if the DNA is condensed, then the index goes up higher, and if the DNA is opened up, it might be less dense. The bilipid membrane has a fairly large index of refraction, but it's responsible for very little scattering because it's so thin. It's only about 5 to 8 nanometers thick. A melanin has a very high index of refraction, so high that under certain conditions, the scattering properties of melanin actually are stronger than the absorption properties of melanin. So even though what we see with our eyes when we look at a person and when we see skin color might relate to the absorption properties of melanin, the scattering properties of melanin can actually be measured, and it turns out it's actually diagnostic if you want to try to diagnose melanoma. It's an interesting phenomenon because they come in little granules in melanosomes. But we want to know how deep do we want to probe. So we can study this dance of light, but how deep do we want to look at the photons that went really deep or only the ones that stayed near the surface? And in order to answer that, we want to know what is the physiology here. And again, it's a physicist's oversimplification, but let me start off by telling you that 85% of all cancers are epithelial in origin, which means they begin in the surface layer of cells that define what that organ is. And those types of cancers are referred to as carcinomas. So this encompasses all of the big name cancers that we all are familiar with. Lung cancer, prostate cancer, breast cancer, colon cancer, stomach cancer, cervical cancer, bladder cancer, on and on. All the hollow organs and most of the solid organs as well are epithelial in origin. Those are called carcinomas. The other 15% are sarcomas, lymphomas, leukemias, diseases like that, and mixtures of those. But carcinomas really are the big ones. And what's interesting is that, therefore, the cancer always begins in the epithelial layer, and the epithelial layer is very thin. It's only 100 to 300 microns thick in most cases. You have this, you might have a layer of crud on the surface. It could be mucus or it could be dead cells if you were skin or whatever. And then you have your epithelial layer of cells, and the detailed nature of these cells is what defines the organ frequently. So the columnar epithelium of your colon is what defines how your colon works, the mucosal layer of your colon is what defines how your colon works. And then below that you have this thing called the basement membrane, and below that there might be a smooth muscle cell layer or layers that they refer to as the stroma. But all the action in early cancer occurs here. So we want an optical geometry that is succinctly sensitive to only that layer if we want to catch early cancer and pre-cancer. So what we're looking at is something like this. And again, this is an oversimplification, but it's meant to illustrate the different stages of disease. In this case, what it's depicting is something referred to as a transformation zone of the cervix, where it goes from a columnar epithelium to a squamous cell type epithelium, and that's the zone where almost all cervical cancer starts. In that area, if you were to look at the progression from normal epithelium, where you have a joining or overlapping of columnar and squamous epithelia, you might look like something like this if you were to make a cartoon out of a histology slide. And then as you go through different grades of dysplasia, from mild to moderate to severe dysplasia, you would see an increase in the size of nuclei, and an increase in the crowding of nuclei in the cells, and size and crowding of the nuclei in cells. And you get to a point where the doctor might want to tell you it's cancer, but it's often referred to as carcinoma in situ because it hasn't yet invaded beyond the basement membrane until it finally invades, and that's when it's called cancer. But at this stage, you want to deal with it. And in some diseases, in some parts of the body, you'd like to deal with it as early as this stage, because if you catch it at this stage of dysplasia, before it's become invasive, it is almost always curable, or at least long-term life extension. So this is what the pathologist actually looks at. So this is some histology of colonic mucosa from the colon. It's a columnar epithelium, so these are, because the cells here in this type of epithelium have the shape of columns, and they line these undulating things called crypts. And mostly what you're worried about is things at the base of the crypts where cancer tends to begin. And here you see a transition looking at a different plane. So if I take, this is a cross-section where the surface of the colon is like this. So this is the mucosal layer, and this is the hollow organ is up there. If I took and did a slice like this, then these crypts become circular indentations going into the mucosal layer. And this shows a transition from normal mucosa, normal epithelium, to dysplastic. You see the increased number and density of the nuclei, and we've expanded and enlarged this here with a higher magnification. You can see that the nuclei, which are these dark purple things, are highly densely packed and overlapping each other and becoming somewhat chaotic. That's evidence of severe dysplasia in colon before it's become cancer. It hasn't invaded the basement membrane yet. So the question is, would this type of epithelium scatter light differently than this? And would we be able to measure that with a simple spectroscopic measurement? So we use an optical geometry that is friendly to the clinical application. It's designed in such a way that you can bring the probe to the surface of tissue, because we want to probe that surface area of the tissue. And don't worry yet about solid organs like breast or prostate. We'll talk about them later in the talk. But if it's a hollow organ like the colon, we can get there with a fiber optic probe, and we make the geometry such that these fibers are small and very close together. So the separation of these fibers is less than 3/10 of a millimeter, so 300 microns or less. So these source and detector are very close together. So most of the light that's collected by the collection fiber are photons that have scattered a small number of times, 2, 3, 4, or maybe only one time, whereas photons that scatter a larger number of times propagate a significant distance, typically are lost. They either come out somewhere else or get absorbed down below there. But if it happens to turn around 180 degrees within a small number of scattering events and gets collected, then we're actually becoming very sensitive to the details of the scattering mechanism. So we use something called me theory to help us understand the analysis, to analyze what's going on in this scattering. So what we're trying to understand is not only the probability for scattering as a function of wavelength, so this is this thing called the scattering efficiency, but also the angular distribution for that scattering, because if it can scatter more at large angles, then we're more likely to collect it than if it scatters only in a forward direction or near forward direction. So there are two things we're trying to understand. One is this thing called the scattering efficiency, and the scattering efficiency is what determines, in physics speak, the scattering cross-section. The scattering cross-section is simply the actual physical area of the particle times this thing called the scattering efficiency. And then when light does scatter, you want to know what's the probability that scatters, let's say, at this angle compared to that angle, that angle. There's this probability distribution for the scattering angle, as we sometimes refer to as the phase function, or the scattering probability, is a probability per unit solid angle steradian, and it tends to be normalized such that the probability of over all angles simply adds up to 1. So therefore, if it scatters, if you integrate over all angles, the total probability ends up being 1. So we use something called me theory, as I was saying, because it tells us why the wavelength dependence of scattering would change with changes in the micromorphology of tissue and the sizes of organelles and things in the tissue. So what is this all about? It's been around for more than 100 years. It has to do with solving Maxwell's equations for a homogeneous sphere in an isotropic medium. Again, we're physicists, so a physicist's interpretation of a chicken is a sphere of uniform density. And we're oversimplifying things, but it gives us a qualitative phenomenological interpretation of what's going on. And actually, under the right conditions, it gives us quantitative information as well. And I'm pleased to say that a couple of my colleagues in the audience are some of the world's experts on extracting that kind of quantitative information. So the way this works is it expands the fields, both the incident field, the field internal to the particle, and the scattered field as an expansion of vectospherical harmonics. And then you simply require the boundary conditions that the tangential fields at the surface of the spherical particle be continuous across that boundary. So you do that, and you can plot, for example, at some distance. So if we were to plot field lines for the different spherical harmonic modes of that particle, at some, let's say, distance, imaginary sphere surrounding that particle, we can draw the transversal magnetic and transversal electric modes. And you can sort of see that, this is the electric field of a radiating dipole, that the dipole moment for the electric field, as you see, imagine a sphere and what those lines would look like. You can see it kind of translate from one to the other. I'm not going to spend too much time getting too deeply into this because I'll lose myself as well as losing some of you. If one wants to be really rigorous and recognize the fact that the chicken really isn't spherical and it isn't really uniform, you can use something called finite difference time domain for calculating how an arbitrary shaped and density distribution particle will scatter light that impinges on it externally. And that's done by making every little element of the scattering thing into its own little radiator and adding them up. And this tends to be computationally very, very tedious, but it is very accurate. Because of the fact that it's computationally very tedious, people don't usually use it, and it doesn't really end up teaching us much more than the simplistic me theory does. So again, what we want to know is we want to know the scattering efficiency as a function of wavelength, because that's going to give us information about the particles we're looking at, and the phase function, the angular distribution. So the important parameters in me theory, when we apply me theory, are the two things that measure what these particles are. One is the size of the particle, and the other is the density of the particle. So the size of the particle is determined by this thing called the size parameter. It's just the ratio of the radius of the particle to the wavelength of light. And these are just constants, 2 pi times the index of refraction of the particle. Okay? So what this is this is saying that I'm measuring the particle with the ruler. And how big the particle is depends on the size of my ruler. So what matters is how large the particle is compared to the wavelength of light. Wavelength of light is my ruler. So if I were to want to study the scattering properties of a basketball, I might use radial waves because there's a large waves and the basketball is large. But if I'm looking at things like mitochondria and organelles inside cells and nuclei, then I'm going to use wavelengths of light because they're on the order of, or maybe a little bit bigger than those sizes, or maybe even smaller than those sizes of those particles. So that's the measure of the size. And the other thing I want to use is the relative refractive index. So a dense particle, a particle that's got much more mass density to it, will scatter light more efficiently than a particle that's not much different in density than its surrounding medium. It's like, think of it as a grain of sand. A grain of sand suspended in water will scatter light more efficiently than a grain of salt suspended in water before it melts, before it dissolves. So we set up an optical geometry where it's all defined by the plane of the scattering. So you have light that comes in from a source, it scatters off of a particle, and you look at the light that comes off at whatever that direction is, choose some direction, and whatever that direction is, that sets up a coordinate system, which we call the scattering plane. And so all the math that I'm going to numb your minds with for the next 2 minutes, I promise you it won't be more than 2 minutes, is all based on this type of a coordinate system that's set up in the plane of the scattering. So we set up a scattering matrix that relates the scattered field to the incident field through a scattering matrix. And those of you in electrical engineering and physics will recognize that this is simply the spherical propagating term that tells you how things lose amplitude as they propagate outward spherically, part of the solution to the spherical wave equation. And the question is, what really happens here? So one of the things we note is that these elements here, these off-diagonal elements of the scattering matrix, should be 0 because the particle, we said that we simplified it, remember, the particle is spherical and it's uniform, it's isotropic. So there shouldn't be any off-diagonal elements. So those become 0. And then the other thing we remember is that when we're a distance away, we're not actually going right into the particle to measure things. We're measuring things at some distance away. Then we measure intensities. We don't measure electric fields. And intensities mean that you square those terms. And so this ends up being a scattering matrix to relate the light that goes in to the light that comes out. And then this is what I spend 2 weeks teaching in my class when I teach this in my graduate course, but I just want to show you briefly for those who really do appreciate some of the cool math. So what we do is we do an expansion of spherical harmonics based on Legendre polynomials. And so the expansion terms are this pi and tau elements, which are the Legendre polynomials plus the angular information and the derivative of the Legendre polynomials with respect to angle. And then you have these expansion coefficients, the A and B coefficients. And that's where all the action is. So we have these expansion terms and the expansion coefficients, and they become this messy expression. But note that these expressions depend, in addition to the Bessel functions, spherical Bessel and Hankel functions, they only depend on those two parameters: the size of the particle, alpha, and the density of the particle, m, the index of refraction of the particle divided by the index of refraction of the surrounding medium. So the ratio of the density of the particle to its surrounding medium, and the size of the particle. So you have these alphas and m's throughout here. Those are the only parameters that actually affect the outcome. So here's the bottom line. Here's the end result. We come up with this scattering efficiency, this Q value, as a function of the size parameter, alpha, and the index ratio. Now this looks mind-numbing, but I'm going to tell you that in a minute you're going to understand, if you didn't already know, why the sky is blue. Because the alpha term, remember, is the size parameter, the ratio of the particle size to the wavelength of light. If the particle is very small compared to the wavelength of light, so let's say it's 1,000th or 100th the size of the wavelength of light, then this alpha parameter is a very small parameter. Consequently, these terms in this expansion that goes on for a ways, this alpha squared term and this alpha to the fourth term, become negligible compared to 1. Everything else that's multiplying them is of the order 1, so this term here is much smaller than that term. So you can ignore all those terms, you end up with the 1. So if you end up with the 1, that means it's all the actions up front here. And if all the actions up front here, that means you have this alpha to the fourth dependence, which means that the scattering efficiency depends as the negative fourth power of the wavelength of light. So blue light has a short wavelength, red light has a long wavelength. What this means is that blue light scatters much more efficiently than red light when the particle is much smaller than the wavelength of light. That's why the sky is blue. It's called Rayleigh scattering, because the sunlight hits the upper atmosphere and those molecules are much smaller than the wavelength of light. The blue light scatters more efficiently. You see this blue sky. Now, if you happen to be late in the day, people living at earlier longitudes see the blue sky, but a lot of the blue light is scattered away, so what's left behind is the red light, and you get this red sunset. So just to demonstrate this for you, I've brought with me a bottle of sky, or a graduated flask of sky, and I hope to convince you. Let's see if I can do this little trick that the IT guy taught me. So my intent is to convince you that you really can get this scattering effect. So you'll see here, it's hazy sky. Okay? I have a white light source, and it's unfortunately not as white as I'd like it to be. It doesn't have much blue light. And I have another white light source, which unfortunately doesn't have much red light, but we'll try both and see what happens. So this light source, you can see that the backscattered light is kind of bluish. It's got a bluish tinge to it. But if I go through a long distance, I get the blue light scattering at the beginning and the red light is what's left over at the end. Can you all see that? And if you want to see the red sunset, and if it doesn't spill on me, can you see the red sunset? Or the red sun? I know, I can't see it. Somebody tell me, you can see it? Cool. Okay. And so if I use a light source that has a little more blue light and much less red light, I really get the blue glow, but it only becomes orange by the time it gets down there, because there's not much red light in this LED light source. Okay. So much for the fun and games. We really want to get to biology, because now that I've shown you all this cool, fun stuff, I'm going to tell you that the Rayleigh scattering is not interesting. And we don't use the Rayleigh scattering because that's a very simple power law, this lambda, 1 over lambda to the fourth. What we're really interested in is these terms that are these complicated terms, because these terms offer the complexity that provides information about the size of the particle once the size of the particle is more than a small fraction of the wavelength of light. So we go ahead and we run this theory and we do some calculations. So this shows, this is the visible range is 400 nanometers to 700 nanometers. That's violet light, blue light, green light, red-orange light, yellow light, red light. And then near infrared and near ultraviolet over here. So you see here, these are the scattering efficiencies for a 3 micron diameter particle and a 0.5 micron diameter particle for two different values of m, that ratio of the relative refractive index, for two different densities of the particle. And so, okay, this is all still nice theory. We got to progress now. And then the angular distribution of scattering is also a very complicated function. And in most cases, when the particle is on the order of or smaller than, on the order of the wavelength of light, the size of the wavelength of light, you get a scattering pattern probability that's rather complicated. I didn't draw it very well, but if this is a polar distribution, so let's say the particle is sitting right here at the origin here, and light is coming from the left, then if you ask for the probability distributions, more of it's near forward, but there's these lobes of scattering at other angles in other directions, and these details really are very valuable in determining which wavelengths you collect in that optical fiber probe like I depicted. So they're very valuable. It has to do with interferometric effects of things going on in the particles. So we go and do some more experiments that are physicists' idealization. So physicists like to set up idealized conditions so they can test their theories. So these bottles have particles in them, suspended in water, floating in water, but each bottle has only one size particle, and the different bottles are different sizes. So these are 33 nanometers, and these are 300 nanometers is 0.5 micron, 3 microns, 4.5, and close to 10 microns. And you'll notice that in diffusely scattered light, just sitting in the room on the table, they all look like milk. They all look white because these are polystyrene spheres. They don't absorb any visible wavelength. So there's no absorption going on. And it just means that all wavelengths of light will eventually scatter back out. And therefore, if you put in white light, out comes white light. Okay? So they all look white, even though they have different sized particles. But if I put that fiber probe, if I use this geometry, which is sensitive to high angle scattering events, and therefore sensitive to the wavelength dependence of changes in particle size, I don't get back white light. I get complex spectra coming back. White light, remember, is all colors of light equal, all wavelengths equal. So I would expect to have a straight line if I was really getting back white light. But when the geometry is such that I showed you with the fibers right next to each other, I get these complicated patterns. So this is, let's see, green is 0.5 micron diameter, red is 1 micron, and the other is 3.7, and blue is 1.7, 3.7, sorry. And so you see these vary, and it's not just one is more than the other, they vary. And this complexity is what yields the information that tells us about micromorphology and pathology in tissue. And we can't totally ignore absorption, because this 800-pound gorilla in your body is hemoglobin really absorbs light at certain wavelengths very strongly. So this is the absorption spectra of oxy and deoxyhemoglobin, and this pale yellow area is a visible spectrum. So if you've ever gone to the hospital and you see this thing clipped on the finger of a patient sitting in a hospital room, and it might be glowing reddish a little bit, or you might not see the glow depending on what company made the thing. It's called a pulse oximeter. It's measuring the oxygenation of the hemoglobin in the patient's blood by looking at 3 or 4 different wavelengths in this zone here, where light very easily gets through the finger. The red light that I was showing here before got through fairly easily. This gets fairly easily. And it's taking advantage of this thing called an isosbestic point, where the absorption coefficient of oxy and deoxyhemoglobin are the same. And so it's like a nice pivot point, a measuring point. It has to do, it means that at this wavelength, at 800 nanometers, the absorption coefficient is independent of the stoichiometry of the hemoglobin. So they can tell whether the patient's oxygenation is going up or going down. Things don't work very well to give you an absolute value, but once you calibrate it for that patient, they do a pretty good job of telling you whether it's going up or down. So, well, but how deep do the photons go? We want to know how deep they go, not just how they scatter in one single scattering event. If we collected the photons in the collection fiber, how deep have the collected photons been? What is their visitation history? So for geometries where the source and detector separation are very small, like I showed you, we use Monte Carlo techniques, which is basically a randomizing thing. It studies random events, just like spinning the dice or rolling the roulette wheel. It studies random events. What we do is we launch photons from that fiber, and we track where they go, and we collect the photons that reach the collecting fiber. The ones that don't reach there, but we collect. And we ask them, if we do this a lot of times, because most of the photons don't get collected, we can ask then statistically, where have the photons been? And so you can get a plot that looks like this. We refer to this as the voxel visitation histories of the collected photons. So if my source fiber was here and my collection fiber was here, I get this volume that we sometimes refer to as the photon banana, where the photons that got collected have gone through this sort of banana-shaped zone. And again, 99% of the light isn't shown here. 99% of the light simply diffused down into the tissue, got absorbed somewhere or lost somewhere else, but didn't get collected. But if it got collected, this is where it's been. And so this gives us an idea that we're probing the depth that we want to probe if we do a good job of putting in the optical properties of tissue to calculate this. So now we're going to get closer to the real clinical application. And I'm running way behind where I thought I would be. So hopefully I'm not putting you all to sleep. I'm going to move a little faster now. So we put this whole system into a box that we can take to the clinic. We have a light source. Light goes through one fiber. Light's collected from another fiber. It gets measured by something called a spectrometer, where the different colors of light are measured by different detectors. And then you plot it all out on the screen of a computer. And we build it all into the computer, for the power supplies and everything. Into this box, together with its computer to control everything. And the fiber optic probe hooks into those little red knobs there. And we take it to the clinic, and we give it to our clinician friends, like Dr. Satish Singh, who's sitting in the audience. And he goes and tortures patients with this. Well, we give them some probes, too, to make it minimally invasive, non-invasive. So we have fiber optic probes that are flexible to go through endoscopes, or we have needle probes that become invasive and go into solid organs like breast or prostate. And even better yet, to make it clinically friendly, we actually build them into the tools that the doctors already use. So this jaws of death looking thing here may appear to be huge, but it's really only a few millimeters across. It's a forceps that fits through the working channel of an endoscope. And Dr. Singh uses this tool normally to get a little 1 or 2 millimeter bit of tissue from your colon to send it to the pathologist and find out whether or not that tissue was dysplastic. We've built into the tool, because Dr. Singh told us we really need to build these things into the tool so that it doesn't have to slow down his work and get the patients going through it at a good rate. So we built the optical fiber probe into the tool, and you can see the little ends of the fiber probe there. And he says, well, for bigger polyps, we also have snares, so we built it into the snare tool. This is a snare tool that's going in to cut a larger polyp in someone's colon, and then that polyp's going to be retrieved and sent off to pathology, but you could simply make a measurement on, determine whether or not it was a malignant or not malignant or pre-malignant before you even cut it. And so we build the light source into those things as well. And then we go and actually do clinical studies. So our colleagues in London have done this clinical study shown here, and Satish has done lots of clinical work in colon and also now in the upper. So these are measurements in someone's esophagus. When you get chronic acid reflux, and you don't take the purple pill, so you get lots of acid going up in your esophagus, especially over a certain age or under various conditions, you can develop a condition called Barrett's esophagus, which is potentially pre-malignant, has a higher risk of cancer, and they need to study this condition to see whether or not there are areas of dysplasia, pre-malignant conditions. So typically what they do is they go in there with their alligator clip, jaws of death, grab a bit of tissue and send it off pathologist. But if we can make an optical measurement, and this was done, these photographs were taken before we built this into that, we would be able to make many measurements on many sites without having to cut so much tissue, and only cut the tissue where it really is suspicious. So here's one of our colleagues putting the probe in through the endoscope that's going into someone's esophagus. And we get back spectra that are indeed distinguishable between dysplastic and non-dysplastic Barrett's epithelium in the esophagus. Dr. Singh has done a larger scale study in the colon, and this is actually old data. I think he has more than 200 patients by now accrued, and at 2 different clinical sites, the BU Medical Center and also the VA hospital. And in our case, we did this with 3 independent GI pathologists because the pathology isn't a rock-solid gold standard. And I'll get to that in a minute. Data were collected by 10 different operators. By operators, we mean the endoscopy fellow of the day. We didn't have PhDs in there running the machine. The doctors are taught in a matter of 15 minutes how to use the instrument, and then they use it. They have a foot pedal, they make the measurements, and they send us the data files. So the training, it's user-friendly. It works in the clinical flow the way the doctors like it. And we use these novel statistical tools that a recent graduate student who is now a postdoctoral fellow with us, Dr. Rodriguez, has developed to cleverly extract the information we need and do the diagnostic classification. So prospective data, we get spectra that look different. We get values of sensitivity, specificity, positive, negative predictive values that are in the 80s to 90s. And these are actually really good values. You might say, well, is anything less than 100% good enough? And then you have to remember, we determine these values, these statistics, by comparing to pathology. And if you ask how good is the pathology, pathology is about 85% reliable because you give the same slide to 10 pathologists, and you're lucky if more than 8 of them agree on the outcome of that slide. So we believe we're as good as the gold standard we're measuring against, and only long-term outcomes can tell whether or not we're better. Really what we want is good negative predictive value. We want to say, if we say that it's negative, high confidence level that it really was negative. So we have explored this in breast cancer. You might ask, how's that done? You stick in a needle. So we wanted to maybe improve on transdermal needle diagnosis to get a better volume sensitivity and a fine needle aspiration. But the doctor said, no, we don't want that because we do large core biopsies in the breast, and that's all that's acceptable to us. But what we do want is the ability to distinguish resection margins during surgery to make sure we didn't leave cancer behind, because 30% of the time they find out they have positive margin, they have to do another surgery and take more tissue out when they thought they had a focal lesion. And they'd also like to be able to assess the lymph nodes to see if it has metastasized during the surgical procedure, not later, during the surgical procedure. So we've studied this, but it turns out it's a real challenge. Why? Because the normal breast is optically very complex. It's not one kind of tissue. It's got the glandular tissue, the glandular lobes of tissue with their epithelial layers on the little lobes of the glandular parenchyma. We also have adipose tissue, meaning fatty tissue, which is different kinds of cells, and we have connective tissue and collagen and things like that have different properties. And then the composition, relative composition of different components changes as a function of time, because it changes with the menstrual cycle and it changes with the menopausal status. So at different times of the month for premenopausal women, the optical properties of the breast varies, and then across menopause, before and after menopause, the optical properties of the breast varies as the relative proportions of different types of tissue change in the breast. So it's a challenge to even determine what's normal, or meaning what's benign. And then the disease is complicated too, because it's not one disease. Breast cancer is several different kinds of diseases. Now these 3 account for probably more than 90% of breast cancers, but even so, there's 3 different kinds. And there's a number of smaller percentages of other types of breast cancer. And so can we distinguish? So of course I'm showing the best data, but we get spectra that typically look like this for normal tissue, normal breast tissue. We get spectra that frequently look like this for tumor, and we get for malignant tumor, for cancer, and we get spectra that look different for benign tumors. So young women frequently get something called a fibroadenoma, which is a benign tumor. By a benign tumor, we mean something that does not have the capacity to metastasize, so it won't be life-threatening. And it does look different from a malignant tumor. And then we've also explored the lymph nodes, and I'm going to just quickly tell you that when cancer does spread, it tends to go initially to something called the sentinel lymph node, the guardian lymph node, the lymphatic chain that drains that tissue. And if that lymph node does not have cancer in it, then it's generally assumed that it's been confined to the region of the original tumor. But if it does have cancer, then they have to also remove the chain of the axilla, the axillary lymph nodes in the armpit, as well as do a radical mastectomy and sometimes the pectoral muscles. And so this is, you'd like to avoid that, and so you need to determine whether the sentinel node is metastatic or not. And this simply says what I just told you. And we have been successful in distinguishing positive from negative sentinel lymph nodes, and this has been studied in over 140 patients in London as well. So that's looking promising. But even also exciting is something that's just been developing very recently, so recent that it's not published. We haven't published this yet. And this question is, can we do something in the primary care physician's office that can assess cancer risk, especially in this particular case for colon cancer? So right now, there's really nothing they can do in the primary care physician's office. They do occult fecal blood measurement. They stick a finger in the rectum and get a little dab of feces, and they put it on something that looks for blood in the feces, and that's maybe about, 20% efficient sensitivity or something like that, or less than that, Satish? Then recently, something very suggestive has been published by Vadim Bachman at Northwestern University in the Department of Biomedical Engineering, their colleagues at the medical school, wherein he reported something referred to as a field effect for colorectal cancer, where a simple optical measurement in the rectal mucosa, just in the rectal region, can tell you whether or not this patient has a polyp that is adenomatous or a cancer somewhere else in the colon, even though the rectal mucosa is normal, at least normal by the standard histopathology assessment from a pathologist. Okay? So he used a method called low coherence enhanced backscattering spectroscopy, which basically extracts similar information to our method. It's just a different type of geometry, a different way of selecting the depth of sensitivity, but it's basically scattering spectroscopy of the tissue. And he noted that the signals correlate with the presence of adenomatous polyps elsewhere in the colon. And I think, should I say proximal colon? Proximal colon, not just the colon. So 40, 50 centimeters away, there might be an adenomatous polyp, and you can tell it by making a measurement in the rectal mucosa. This is very controversial, first of all, and it's very suggestive. But we then asked the question. I said, ask Satish. I said, Satish, do you think we could make these measurements? He said, we already have made these measurements. We just never analyzed it for that. So he gave the data. So what the problem is that no one has validated the work by the Northwestern group yet. No other group at any other center has validated this work. Mostly because they can't make the measurement that he can make. It's a relatively subtle optical measurement that he makes. But we realized that we already had some of this data. So I'm going to tell you. So yeah, and if this field effect could be confirmed, it would really have a high impact on the management of colorectal cancer. Because you wouldn't have to go for colonoscopy for your screening. You would only go for colonoscopy if the simple measurement done in the primary care physician's office told you you have an adenomatous polyp, you need to go get it removed. So it turns out we already had the data because Satish has been playing with our toys and was making measurements along the way in the normal colon before he ever got to a polyp. And so we gave the data to Eulalia Rodriguez to analyze for us. And then more recently he started making measurements as soon as we decided, well, this might be interesting, started making measurements in the rectal part of the mucosa before getting and we did a simple fitting of principal components that Eladio did, and we found that indeed they separated rather nicely. From those, these are patients who somewhere in the colon had an adenomatous polyp versus patients who did not have an adenomatous polyp or only had benign polyps, hyperplastic polyps. Now this is retrospective and it's a small number of patients, so don't go and tell anybody in the press about this because we'll just get in trouble. But it is suggestive that there are interesting things that we can be sensitive to that histopathology won't even see. And it may well have to do with things that are smaller than can be resolved by a microscope or that are traditionally not looked at by histopathology. For example, things like the blood perfusion around the crypts. So anyway, we do actually translate our spectra into actual physical quantities frequently. And so we can do that. We can learn about the scattering intensity of the patients who had adenomas from those who didn't, or things that have to do with the size distribution, or things that have to do with how much blood perfusion there is in the vicinity of these crypts. Now I'm going to tell you about some of our spin-offs. And I know that Christine is cringing there because that's a picture of it. So there are all kinds of other really cool things you can do with light. Now closer to elastic scattering spectroscopy is Christine's PhD topic, which is to use light scattering, and this is a collaboration with Dr. David Waxman in the biology department, to study apoptosis in cells to see if we can measure early things and different pathways and monitor different pathways of apoptosis in cells. What is apoptosis, for those of you who aren't familiar with the cellular biology, is the natural method of death of cells, programmed cell death. It's a natural way your body replenishes old cells. Typically 1% of the cells in a given tissue organ are undergoing apoptosis at any given time. The body comes and takes them away, scavenges them away. The little garbage collectors come and take them away, and then you grow some new cells. But it's also the predominant response to most cancer treatments. Most cancer treatments induce massive apoptosis in the tumor if it's successful. And so understanding apoptosis is pretty important. There are thousands of papers published annually. There's a whole journal dedicated to apoptosis. So understanding the pathways and having easier user-friendly ways of monitoring them would be valuable. So this is the topic of her project. But otherwise, she does this. She works in the lab because she loves to kill cells. I mean, that's a real reason. And she does this by shining light on cells in a culture plate and looking at the spectrum that comes back while doing things to these things chemically to induce apoptosis with drugs that might be used for chemotherapy purposes. And she sees changes in the spectrum coming back at very early time points and increasing at later time points that relate to the progression of apoptosis in the cells. And we're getting kind of excited about it. We're getting in over our heads because the biology is really complicated, but there's lots of work for future students as well to do here. And then there's another student's been working on using light to do other things, and this is Kurt Schoner, who's been working on using light to image and sense the traveling of a nerve impulse through nerve fibers, otherwise known as the action potential propagation through the axons of nerve fibers. And he does this by taking shining light through a linear polarizer, through a nerve fiber, then a cross polarizer, and then a detector. So what he's looking at is the extent to which this nerve fiber changes the polarization of the light due to a property called birefringence. And the fact that the electric field of the action potential propagating through this nerve fiber can change the birefringence is rather interesting observation. And so what he does is he takes the nerve fiber, the nerve bundle from the walking leg of a lobster, keeps the lobster in this cold tank, takes the nerve from one of the legs and puts it in this chamber here with the fluid that keeps it alive, stimulates electrically one end, and then this thing propagates, and he watches it optically. And we really know he's in the lab because he loves to eat lobster. Because what does he do is after he's used up the legs of lobsters, he takes them home and he cooks them. And he's seen some really cool stuff. He's actually been able to show and explain, he just defended his PhD thesis a couple of weeks ago, that the temporal shape of the action potential seen depends on the distance from the stimulation point, especially when you have compound action potentials in these complicated nerve fibers that have different size axons. And this is something that's a bit at odds with the established wisdom in the published literature as to why we see what we see in the action potentials of these nerves. And then there's Catherine Calabro, who's doing a computational thesis. And since you can do computational work anywhere, you don't have to be in Boston to do, because you're not doing experimental work. This clearly was not taken in Boston. And what she's been doing is developing computational methods to extract the optical properties from the spectra and also to model where the light goes, but putting in the real complexity of tissue with layers of tissue that, tissues tend to be layered, and the different layers have different optical properties, and there's heterogeneities in the tissue. She plugs all that in. Of course, this is complicated computation. And in order to do that with a reasonable amount of time, you want to develop parallel processing methods. So she's been developing methods of doing massively parallel processing for the simulation of our optical propagation methods using video boards. So it's obvious that the real reason she's in our lab is because she loves to play video games. Then we have some of our postdoctoral fellows. This is Dr. Ergin, Dr. Ayşegül Ergin, and she's been working with collaborators. So in addition to measuring the scattering properties, we can of course also measure the absorption properties. And if we change our geometry, we can be very sensitive to absorption properties in the tissue and reduce our sensitivity to the scattering properties. And so she's been studying optical pharmacokinetics, where she measures the concentration of drugs in tissue in real time. And she's collaborating with a colleague at the Columbia University Medical School who's been developing novel methods of delivering chemotherapy agents to brain tumors, because chemotherapy agents have a hard time getting across the blood-brain barrier to get into brain tumors, and he's developing new methods to do that. But in order to check whether or not they're working, you have to see whether or not the drug actually gets into the brain tissue and whether or not you've properly disrupted the blood-brain barrier. So she's working with Columbia University colleagues in doing that, and clearly the reason she's working with us on this is because she really loves drugs. And then we have Dr. Osama Amar, who's been working with me for a good number of years. He's a senior research associate and also an instructor. He's been teaching courses for the BME department. And he's been designing, he's our wizard in making tools and instruments that actually work and things that actually work in the clinic. So he's really good at building the instruments, designing and building instruments for the ESS to actually work in the clinic, novel tools and instrumentation. And so we really know that he really has his fun, because he loves high-tech toys. And so the bottom line here is that none of this happens unless you have really good collaborators and students. And so I've been blessed with a great array of students over the years. It's one of our recent parties in my house, and a great array of collaborators. So this is a recent symposium we had here in this building. Up on this picture's taken on the 7th floor, a symposium of our multi-center, multi-national collaboration a couple years ago. They all congregated here for the study, and some of these people are names I've mentioned. There's Dr. Singh, there's Vadim Bachman, there's a famous professor, Tayaba Hassan from Harvard Medical Center, MGH, I'm sorry. I think Lev Perelman's in the audience. There's Lev. And there's a few other people who have collaborated with us or worked with us or advised us here. And of course, all the clinical collaborators in the actual medical centers. And so I'm sorry I've taken so long and gone way past my allotted time. And I know the real reason you came here was for the wine and drinks and food upstairs. So please do join us upstairs on the 9th floor. And I thank you for coming and honoring me with your presence here.